In late 2000, a star system 20,000 light-years from Earth erupted with enough force to launch material outward at nearly 3% the speed of light. For over 2 decades, nobody could see what actually happened at the center of that explosion. A wall of dust, thrown up by the eruption itself, sat directly in front of the evidence. This year, using 4 different telescopes working together, astronomers finally got a clear look. What they found wasn't just an answer. It was a new question nobody had thought to ask, because nothing like it has ever been documented in any other stellar explosion. The object is called V445 Puppis, and it holds a specific, narrow distinction. It is the only confirmed helium nova in the entire Milky Way. To understand why that matters, you need to understand what a nova actually is, because the word gets thrown around loosely, and most of what people assume about it is wrong. A nova is not a star dying. That's a supernova, a completely different and far more violent event. A nova happens in a binary system, 2 stars orbiting each other, where one of them is a white dwarf. A white dwarf is what's left after a sun-like star runs out of fuel and sheds its outer layers, leaving behind an extremely dense core, roughly the mass of the sun, compressed into something the size of Earth. On its own, a white dwarf just sits there, slowly cooling. But if it has a close companion star, its gravity can start pulling material off that companion's outer atmosphere, and that stolen material spirals down and accumulates on the white dwarf's surface. Normally, that stolen material is hydrogen, because most companion stars are still hydrogen-rich, ordinary stars. It builds up in a layer on the white dwarf's surface, compressed by the white dwarf's enormous gravity, until the pressure and temperature at the base of that layer become extreme enough to ignite runaway thermonuclear fusion. The result is a nova, a sudden, brilliant brightening as that surface layer detonates, blasting the accumulated material off into space at high speed, while the white dwarf itself survives intact, ready to repeat the process once enough material builds up again. That's a classical nova, and astronomers have documented hundreds of them. V445 Puppis is not that. Its companion star isn't an ordinary hydrogen-rich star. It's already been stripped down to a helium star, meaning something, likely an earlier phase of mass transfer in this same binary system, already pulled away its hydrogen envelope long before this eruption ever happened. So when material spills over onto the white dwarf, it isn't hydrogen, it's helium, and a helium-fueled thermonuclear runaway is a fundamentally different, much rarer event than a hydrogen one. As John Mills, the University of Warwick doctoral student who led this research, put it, "How could such an event be completely devoid of the most abundant element in the universe?" That's not a rhetorical flourish. Hydrogen makes up roughly 3/4 of all the ordinary matter in the universe. Finding an entire explosive stellar event that manages to happen without it is, on its own, a genuine rarity. Now, back to 2000. When V445 Puppis erupted, it launched what astronomers call a bipolar outflow, 2 opposing streams of ejected material, blasting out from the poles of the system in roughly opposite directions, shaped by the disk of gas and dust surrounding the binary that constrains the explosion into 2 lobes, rather than a simple expanding sphere. That outflow eventually stretched more than 1 trillion miles across, a scale that's genuinely difficult to hold in your head. For comparison, that's several hundred times the distance from the Sun to Pluto, in each direction, and it happened within the lifetime of people currently reading this. But almost immediately after the eruption, something got in the way of actually studying it properly. A thick disk of dust and debris, much of it flung up by the eruption itself, settled directly across our line of sight to the system's center. For more than 20 years, that disk simply blocked the view. Astronomers could see the outer edges of the outflow, but the engine driving it, the actual binary system, and the immediate aftermath around it stayed hidden. This is where the multi-telescope part of the story matters. because no single instrument could have cracked this open alone. Different telescopes see different things, and this particular mystery needed all of them. The European Southern Observatory's Very Large Telescope, working in infrared light, can partially see through dust that blocks visible light entirely, because infrared wavelengths pass through fine particles that would scatter or absorb shorter wavelengths. That gave researchers their first real look at structure hidden behind the debris. The Hubble Space Telescope, working in visible light, had actually already captured images of the outer parts of this outflow back in 2013 and then again in 2015, but those earlier images alone weren't enough to resolve what was happening close to the source. The Southern African Large Telescope contributed spectroscopy, splitting the light into its component wavelengths to identify exactly what elements and compounds were present in the ejected material. And NASA's TESS mission, designed primarily to hunt exoplanets by watching for tiny dips in starlight, contributed precise photometry, tracking brightness changes over time with enough sensitivity to pick up subtle variations tied to the system's behavior. It was the combination of all four datasets, gathered and cross-referenced over years, that finally let the dust genuinely thin enough and let researchers see clearly enough through what remained to resolve what was actually happening close to the binary itself. And what they found sitting inside that trillion-mile-wide bipolar outflow were bullets, discrete, compact, high-velocity clumps of gas, distinct from the smoother, more diffuse material around them, embedded at either end of the outflow, like beads strung along the two opposing jets. Here's the number that makes this genuinely strange. Those bullets are moving at up to 20 million miles per hour. To put that in context, a typical classical nova ejects material at somewhere between a few hundred and a couple of thousand kilometers per second. 20 million miles per hour converts to roughly 9,000 kilometers per second. That's not a modest step up from a typical nova ejection speed. That's an order of magnitude beyond it. Fast enough that these bullets are moving at nearly 3% of the speed of light. Speed alone, though, isn't what's actually stumping researchers. Fast ejecta from explosive stellar events aren't unheard of. What's genuinely unresolved is the clumped, bullet-like structure itself, discrete parcels of high-velocity gas, rather than a continuous, smoothly expanding shell. That structure implies something localized and specific is accelerating pockets of material well after the initial explosion already happened, rather than everything simply being flung out together in one continuous blast at the moment of eruption. Mills was direct about how open this question still is. The origin of these bullets is a mystery. We suspect that these originated post-outburst, but bullets of this kind have not been observed in any other nova. That last part is the detail worth sitting with. This isn't a case of an established phenomenon showing up in an unexpected place. Researchers who study novae for a living are looking at something with no known precedent anywhere else in the observational record. That absence of precedent matters more than it might sound like at first. Astronomy, like most observational sciences, builds understanding by comparison. When researchers find something unusual, the first move is almost always to check whether a similar structure has shown up somewhere else, in a different system, under different conditions, because that comparison is often what reveals the underlying physical mechanism. With V445 Puppis's bullets, that comparison currently comes up empty. There's no second example to check against, no pattern across multiple systems to triangulate a cause from. Right now, this is a genuine outlier sitting alone in the data, and until either a similar structure turns up somewhere else, or someone develops a model that can be tested directly against this one system's specific numbers, the honest answer is that nobody knows why these particular clumps of gas are moving the way they are. It's worth being clear about what is and isn't settled here, because it would be easy to round this up into something more dramatic than it actually is. The eruption itself, the general helium nova classification, the trillion-mile bipolar outflow, The 20-plus years of obscuration by dust and the 20 million mile-per-hour bullet speeds are all measured, published findings, not speculation. What remains genuinely open is narrower and more specific, the mechanism that produces discrete high-speed clumps rather than a smooth outflow, sometime after the initial explosion, in a system whose companion star had already lost its hydrogen before any of this happened. That's a real, bounded scientific question, not a vague appeal to mystery for its own sake. There's also a broader reason this kind of finding matters, beyond one unusual binary system. Novae, in general, are one of the ways heavier elements get seeded back into the galaxy, material processed inside a star, then blasted back out into interstellar space, eventually becoming raw material for future generations of stars and planets. A helium nova represents an even rarer variant of that recycling process, run on different fuel, through a different companion star history than the classical hydrogen novae astronomers are used to modeling. Every detail that doesn't fit the existing framework, including a detail as specific as unexplained high-velocity clumping in the ejecta, is a place where the current models of how binary stars lose mass and enrich their surroundings are incomplete. Figuring out what's actually happening here isn't just about one nova. It's about whether the broader picture of how these systems behave needs revision. For now, the honest position is that the picture is more complete than it was a year ago, but not finished. Researchers have 20 years of accumulated multi-instrument data, a clear structural picture of the bipolar outflow, a precise velocity measurement for the bullets, and a confirmed rare stellar configuration driving the whole event. What they don't have yet is a mechanism. The dust that hid this system for 2 decades has thinned enough to show the shape of the mystery clearly. It hasn't yet revealed the explanation underneath it. If you want to know what turns up when someone finally does explain it, subscribe, because a finding this specific, sitting completely alone in the data with no comparable system anywhere else, is exactly the kind of open question that tends to get revisited the moment new instruments or new theoretical work catch up to it.